Welcome back. We'll see some more examples of the equilibrium. This thing, solids and liquids. We'll see solids in liquids. Every day, everybody is saying sugar water. So add more sugar at higher temperatures. So all the sugar should be dissolved. Now bring it to the room temperature. What will happen? What will happen? Sugar will be coming back to in the bottom of the glass or whatever. That means it is supersaturated. Saturated solution at that particular temperature you make it, and now at the room temperature it is coming back, separated out. So at a given temperature there will be always sugar is going into the solution, and from the solution, sugar solution to the this thing will be coming back to the solid sugar. That can be easily seen by radioactive experiments, but not at the 11th standard and all this. That is the sugar solution. You take one more example. Everybody knows about the soda, particularly the goli soda. So in that, carbon dioxide is pumped in the water more than the solubility and kept the lid as a solid and all these things. Now when it is opened out, what will happen? All the dissolved gases excess at the temperature and pressure, particularly pressure in this case, it will be going out. And afterwards, there will be an equilibrium between the water, that is the distilled water or DM water, and the atmospheric carbon dioxide, and that will be maintained. A dissolved carbon dioxide will be maintained, depends upon so many other conditions, pressure. So, what I meant to say finally, there will be so many equilibriums, particularly dynamic equilibrium. For solid equilibrium, there is only one temperature melting point at liquid vapor equilibrium, that is a boiling point, and dissolution of solids in liquids and dissolution of gases in liquids. Like this, many varieties are there for the this thing in the equilibrium. For general characteristics of equilibrium is one. First, we will see one by one what are the general conditions. Equilibrium, always you remember and by heart. Equilibrium is possible only in a closed system. Open system means you have to go to, particularly ice and water. If you want to say 0 degree centigrade, you have to go to Himalaya or Sonmarg. Okay. That too, it is at a particular or constant temperature. No change in the temperature and pressures. Number 2, it is a dynamic equilibrium. It is a dynamic equilibrium. Looking like the equation is rate is stopped, but it is rate of forward equal to rate of backward. And all measurable parameters or properties are constant. Mainly temperature should be constant. So if you are changing any parameter like temperature and all, you are changing or increasing or decreasing the temperature, either rate of forward reaction or backward reaction will change and again attains the one more new equilibrium. Just for the chemical equilibrium, most of the time this will be used for the chemical equilibrium. Just for the sake of the A and B are the reactants, and how to represent? It should be half arrow. A reversible reaction, it should be half arrow. Normally in this thing it will be a single arrow and whatever the side and all. Here it will be two lines with half arrow should be there, C plus D. This is the reactants, this is the products, and they are in the equilibrium. And means after certain rate of reaction, both the forward reaction is equal to the backward reaction. So if it is to be represented by the pictorial as a time versus the concentrations of the either A or B or what C, initially what will happen? Initially A and B is forming C and B more. That means initially it will be like this, like this, like this, like this, and it will go on this thing. And initially when it is a 0, the initial concentrations of the products is 0. The reactants will be high. This is A plus B. This is C plus D initially. High. So that will be going on, coming down, and attaining equilibrium. The products is the increasing at the time as the time progress, and the reactants are coming down. At particular point, both are at particular point attaining equilibrium. This is the equilibrium time, this is the equilibrium concentration of the products, this is the equilibrium concentration of the reactants. That will be normally this thing. But all these things are at particular temperature and pressure. If I am disturbing this, again this curve, entire things will be either this side or that side, depends upon the other parameters, it will change. Okay, so that will be the normally the, suppose a small example I will take, nitrogen and hydrogen giving ammonia. Balanced equation I have to write. So here this will be a reversible reaction, that means double arrow and with a double this thing. This is the normal reaction. In this normal reaction, how it will looking like? Okay, if I am writing the concentrations, molar concentrations and time, initially the hydrogen concentration will be very high because this is one of the reactants or I am writing. This is hydrogen, and another one is the nitrogen, another reactant. Product is ammonia. Initially it will be 0, after some time it is attaining at a particular this thing. This is ammonia. This is a product, and this will be at the depends upon the temperature conditions and all these things. After some time it may not be forming on all these things also, and it may forming even the hydrogen will become the deteriorated compounds also. That can be seen by mass spectrometers and all these things. It is a chemical dynamic equilibrium at particular composition, particular concentrations and particular temperature, all these things. Okay, tomorrow we will see further. Thank you.